All right, so we're going to start talking about the graphs of quadratic functions. And quadratic functions, we've talked about the three different forms that they could come in, whether it's standard form, vertex form, or factored form. But the graphs of any of these types of functions are always going to look something like this. All right, this is called a parabola. All right, where it's kind of a U-shaped thing. But that's what the graph of a quadratic function is going to look like. There's some important characteristics that we're always going to be talking about or asking about. So let's get to talking about them so that way you're familiar with what they are and not necessarily how to find them yet, but just what they are. Okay. The first one is the direction that they're opening. All right. Whether they open up or down. Okay. This particular one, because these arrows are pointed upwards, all right, this thing is, you would say holding water. This one is opening up. All right, but that's one of the characteristics that are, kind of important. It's a really simple thing to tell algebraically. It's just whether or not this a value right here is positive or negative. That's all you look for. What else? We got the intercepts. It's always a classic. Okay, the x and y intercepts. On a quadratic, these are typically going to have two x-intercepts, but it's the places where it intersects with the x-axis, and of course your y-intercept eventually will happen somewhere in this neighborhood. It's the place where it crosses the y-axis, and those are algebraically not too hard to find. For the y-intercept, you plug in 0 for all the x's, and in order to find the x-intercept, you plug in 0 for y, and then you got to solve that equation. See, what else? We got the vertex. All right, the vertex should be kind of a new one. This right here, that's our vertex. All right, in this case, the vertex is 4, -3. All right, it's the ordered pair that represents like the highest or the lowest point on the function. Okay, that's one way that you could describe it. The highest or lowest point. If it's opening up, it's the lowest point, and so it represents a minimum. If it were opening downward, something like that right there, the vertex would be a maximum instead. Okay. You could also think of the vertex as the function's turning point. All right, it's the point on the function where it changes direction. All right, so here the function is decreasing until it gets to the vertex, until it gets to 4, and then it starts increasing after that. So it's the point where it switches direction. And another little quality that's worth remembering about the vertex is that it is in between, it's directly in between the x-intercepts. Okay. So I don't know what these two values are right here for the x-intercepts, but I know that that vertex is directly in between them. That 4, it's the average of these two x-intercepts. We're going to talk about the domain of a function, right? The domain of a quadratic. For a quadratic, though, it's pretty easy. It's always the same. The domain is going to be all real numbers, or you could describe it as -infinity to infinity. So the domain of a function, it's the set of all possible inputs. Okay, that's the definition for what the domain of a function is. The set of all possible inputs or its x values. Right? And if you look algebraically, there's actually no restrictions for the numbers that we're allowed to plug in for x. And the reason why is you can always take some number and square it. Like there's no rules you're going to break. And then you could take that answer and times it by a, And you can add and subtract numbers. So there's actually never going to be any restrictions whatsoever when it comes to the domain of a quadratic. Stuff that that you do run into issues with, which we'll talk about later, is going to be something like this. This would have a domain restriction. Like you would not be allowed to plug in 2 for x because that would give you a 0 in the denominator, and you can't have that. All right, that's an example of something that does have a domain restriction. The domain, you could also think of it as how far left and right the graph goes. That's another way to think about the domain of a function, how far left and right it goes. That's like its x values. So this thing goes up and to the right forever, it goes up and to the left forever, and so we say it has a domain of negative infinity to infinity. All right. You've got your domain, and you've also got your range. Okay. The range actually, it's going to depend on the vertex. Okay, it's not always the same. It's the set of all possible outputs or your y values. Other way to think of it is how far up and down the graph goes. All right, so for this function, the lowest that the graph ever gets to is right here, which is at -3. That's why it's dependent on the vertex, because your vertex is the lowest or highest point. The lowest it gets to is -3, and the highest it gets to, the furthest it goes up, is infinite. Okay, so for this function, this particular one, we would say it has a range of -3 to infinity. So the range will actually always be different, from function to function, but the domain is always going to be the same, negative infinity to infinity. You could write your answer like this, or you could say the range is, it's y is greater than or equal to -3. That's another way to write that. And I'm putting the little brackets on the -3 because it actually passes through -3. It includes the number -3. But I'm not including infinity because you can't actually get there. Like, it's not an actual number that you can reach. But yeah, those are the, I guess 5, yeah. Those are the 5 main little characteristics that you'll want to pay attention to when we talk about these quadratic functions. We'll go over how to find them given the different form.